Next speaker is Bob Nowack, our colleague, right, to decide.
And now they're both actually at Colorado School of Mines finishing their things with Ruhl Snyder and Taze Wappener and those folks. But we were doing this here kind of with simplified experiments, okay? And hopefully the illustrations will be useful. So the first thing is, let's see if I can get this here. So seismic noise and interferometry. So that's certainly a hot topic, but one that still is deceptively kind of out of reach still. And I'll just talk about that briefly. Then interferometry and Marchenko, which is what both of these guys are wrapping up at School of Mines with Ruhl Snyder and stuff have been doing with 3D. This is just going to be some illustrative things. And then application to carbon sequestration, because that seems to be a theme of this meeting. And so we applied it to some real data, and we'll show it here in a very simplified sense. So let's just do the first one. And again, just as overview, Aki in the 1950s was using traffic noise. Alita was talking about that here in her group as well, to image shallow site structure. And this was later identified as an early application of seismic interferometry by Sanchez-Sesma and Campillo. And I just visited Sanchez-Sesma and UNAM in Mexico City for part of March, which was great. And then other early work, of course, if you're more from an exploration setting, would be Claerbout's stuff. And then interferometry of ambient noise can be used to form images. And this has sometimes been called an early days daylight imaging, because it's kind of what your eyes would see in diffuse lighting in a room, for example. And this is 1990s to 2000s with Richard Weaver at Illinois, our neighboring institution. And he was doing this in the lab. And he basically showed that if you did correlation processing, independent of not knowing what Sanchez-Sesma and Campillo realized, that Aki had actually done this in the 50s, but Richard Weaver was doing this in the physics department in the lab, and basically taking ambient noise signals and cross-correlation processing to get as if you could take one detector and make it into a virtual source, but really you've got noise happening everywhere. And there's a little picture of Richard Weaver here. One of my sadnesses of being at Purdue for a number of years is not really getting to know Richard until maybe 2008 or something like that. And he's still there. He's emeritus at Illinois. So this is just the idea. You've got ambient noise happening everywhere in this setting of interferometry, and you want to reorganize the experiment in such a way that it's interpretable, right? And so here's just Richard's famous aluminum block from his lab, where basically you've got a source and a receiver on some disoriented aluminum block with a hole in it. And I only saw this block maybe about 6 or 7 years ago. And it's famous. You're an expert in interferometry if you've seen Richard's aluminum block. And here it is where, whoops, let me go back. And here's a comparison of an actual source versus virtual sources. And he over a series of papers, calmed down the block more and more and more and isolated it. So it came down to just thermal noise. And that was enough to form an actual image, right? And so again, if you essentially co-locate a receiver, so seismic waves beneath a receiver can be retrieved by converting a co-located virtual source into receiver. And this can be used to perform interferometry of ambient noise to construct an effective zero offset reflection response. And the initial thought was, if the source and receivers are really close, the surface wave hasn't really developed as much in the physical experiment, or at least the thought was. And so this was one of our early experiments. This is with John Oren, who was a master's student here and finished with Jeff Schraga, I think in January, doing similar stuff actually. And so the idea here is that you have kind of reflections in kind of a crustal model, and this is stacking over a day, a month, a year. And again, a lot of people have used this now, and this was 2017, not that long ago. And this was an example of the Rice group with Dung and Levander, and Jonathan was saying that they're using some of your codes for some of this. And this is on Mars. You had one sensor, the InSight mission. What do you do with it that cost $1.5 billion or some such? And you use this exact same processing, and you can come up with a reflection seismogram for an entire planet. Okay. And again, and then after Dung and Vander did this, all of the NASA-based people did 20 papers on doing this stuff, right? Because you don't have that many moonquakes to deal with, right? So, but the question really is, so you can use this for ambient noise, for possibility of doing reflectivity with no active sources. And again, they're expensive, et cetera. And general ambient noise includes both body waves and surface waves. And really the a better separation of that is really needed to improve the results. And it made me thinking about this and these guys in the 1930s and 40s, whether they're in Germany or wherever at the time, or Karlsruhe or what have you. And basically they figured out how to isolate the P wave reflectivity from the ground roll so that you could do P wave imaging. But it's even more astonishing than that, because the coda waves, if you're in Roel Sneeder's lab, and when he did this in the lab himself at the School of Mines, they're all S waves. So the equipetition theorem says after a certain while, all P waves get converted to S waves. And yet the oil industry went exactly the opposite and took everything else out. And so they have 1% of the signal and are getting these reflection images. You know, at least do the S waves, because everything turns into S waves if you're equipetition. Okay. So in any case, this was, I'm just going to show an example picture here. So using, you know, but they used active sources. But to use general ambient noise in a daylight imaging mode, and we have people at Exxon and Shell, for example, you know, to get a similar level of resolution is still an active area of research. And so I'll just give an example of this. This might be a reflection line from from a book or something like that. But this would be from active sources. And the idea is with ambient sources to get a similar level of resolution as this. And this is a few years in the future. And I'm going to guess, with both of you guys being experts on this, I'm going to say, even with Exxon, this is still in the future, but I'm guessing. So I don't know. Okay, so let me go on to the next one. This is Marchenko. And this kind of came out by another person in the Midwest, a guy named Rose, who was over at Iowa State. And he capitalized in this, and Ruhl was smart enough to realize what he was doing and taking it back to geophysics. But let me just see if I can give a picture of this. So the idea here is that you've got an overburden, and you've got sources here, and you've got receivers. You've got a scatter down here that you want to image. That's where your oil is, right? But you've got salt, you've got overburden, and you don't. It's like a distorting lens, and you want to get rid of it so that you can go down here. So the idea is, can I take these guys and make virtual sources underneath this stuff so I can get a better image of that thing? And interferometry can be used for that as well. And so you can do that simply by putting an active source down here, say in a borehole down here, or you can use classical seismic interferometry if you have two receivers down here in a borehole, then to convert one of them into a virtual source. And then you have a little experiment underneath. And then the final thing is to basically use scattering theory, which Marchenko imaging is one flavor of, and to so-called redatum the data down to down underneath here. And that's what I'll be talking about here. So again, seismic interferometry, the so-called Green's function, essentially has a source, and then whatever you record at your receiver would be called the Green's function. And by cross-correlation processing, if you had two receivers down in a borehole, you can then essentially cross-correlate those results from tunnel drilling or whatever else noise and convert one into a virtual. So that'd be almost classical interferometry if one could do that. But then you need actually ambient noise all over the place to make that work. You have to have a so-called diffuse wave field, meaning waves are coming from everywhere to make that mathematically kind of work, right? But what happens if you only have one-sided illumination? You have stuff coming from the top, for example. Then Rose showed at Iowa State in the lab that basically you can use autofocus with just one-sided information coming down and then make a virtual source underneath the defocusing lens or something that's blocking your view of what you want to see, subsalt or what have you. And Broghini, Rule-Snyder, Case-Wappener in 2011 and 12 basically pulled that over to geophysics. And that's why you really need these broad thinking people like Rule-Snyder who can go to the engineering community, grab something and take it back over to geophysics. Okay. Okay, this is just a simple model. And the idea is I've got a source up here. I've got a reverberatory layer here, and I want to image this guy here. So I don't want to have this thing getting in the way. So I want to redatum a source here, down under here, so I can get a little echo off of this thing and make it really clean. That's the idea. It's a simple experiment. And this is what this guy Merck Perez, who's now finishing with Rule at Mines, was doing for his master's. And I'll just be kind of explaining this a little bit. So the idea is with classical interferometry, what I can do is I can take, if I had like a borehole here with receivers in the borehole, I could then convert one of the receivers to a source and then maybe another one here and reflect off that boundary. But I would need waves coming from all directions, which mean top and bottom to make that work. So here's an example. So think of this, to kind of tune your mind a little bit to this, but this would be a borehole going down with a bunch of receivers in it. And this is in time. And here's a source at the surface, and it's reflecting of those various layers. And there's multiples in here. And this is the bottom reflector down here. So this would be if I had something on top, but seismic interferometry says I need something on the bottom as well in this 1D analog. So this would be like I need an earthquake source, or I need something on the bottom of the model. And those two would be needed to do that. And if I do, then here's a synthetic example of a source down here with reflections through here underneath the layer. And then here it is with classical interferometry. Now there's a little shift here because the interferometry gives a symmetric negative time, positive time. But if I shift this down a little, it exactly matches. So that's classical interferometry. But I need an earthquake signal coming from below, in addition to something coming from the top to make that work, and making sure I have sort of what's called a diffuse wave. So this is the example with Marchenko imaging, where I only have energy coming from the top. And I've moved my source down into the medium, and I get basically a similar wavefront just with top going energy. Okay, and that's what the scattering theory allows you to do. Okay, so if I go to the next slide, so Marchenko only requires one-sided illumination, and the virtual source does not have to be at a receiver. Also, the detailed velocity model isn't needed to do this. But I should give a caveat that in 3D, you need estimates of the first arrival times from the virtual source positions up to the receivers. So some smooth version of velocity is needed in 3D. So let me give an example here. So, but then in 2016-17, at Mines in Delft, basically they said, okay, I don't even need a receiver down there. I don't need a source or a receiver down there, and I can move them both down to be virtual, and then make a record section, like a little refraction line, underneath the thing. Okay, and that's called extended source receiver. So let's just try it on the computer. And as it turns out, I get a great result as well. So now in this experiment, my source was originally on the surface. I have no receivers down in the model. And I'm making receivers here, and I get the same thing as if I had receivers here. Okay, and so this is just knowing enough of your wave propagation that you can manipulate your experiments. It's kind of under the broad term of redataming, but again, Rule he brought in all of his inverse scattering knowledge and went out to the literature and found out what other people were doing and took it into geophysics. Okay, so, and this is just an example of, this is if I have a known source at the subsurface at a given receiver. This is if I move the source down and have the receivers known. Here's where, I don't know, oh no, this is interferometry, where I have a source and receiver, but it needs waves from below. This is the source, oh gosh. Okay, this is classical Marchenko. This is extended Marchenko, where I don't have a source or a receiver in a subsurface, okay? And again, and then I can use this for imaging too, because if I move my virtual source and receiver right above a reflector, all the reverberations are gone and I just get an image. So it's an imaging process as well. So again, focusing energy to points in the subsurface without knowledge of specific details of velocity margin are important for potential applications to imaging. When Claerbout, if you go back to history, he basically was moved from 1D scattering to laterally varying media. And he thought about taking sources and receivers and moving them down into the earth as part of his imaging process, kind of phenomenological, which is where Claerbout kind of worked for much of his career. And and then cross-correlating, which is your imaging condition, right? So however, at the time, Claerbout did move to single scattering model, which is called Born approximation, within a now classical migration imaging approach. But both Marchenko redatuming and seismic interferometry allow for multiple scattering in contrast to classic seismic migration. So in some sense, in my view, this puts migration into a much better theoretical framework. And you don't have to take all your reverb out because multiple scattering is perfectly allowed in here. So I don't know, it's exciting. You've seen this at multiple image meetings and SEGs and these, but this is just my simple examples of this. And this is an example to carbon sequestration. And Ajo Franklin gave us some of the data from the Frio experiment down in Texas, which is located here, I guess, in Dayton, Texas. And here's the injection well for carbon CO2. Here's the observation well, and here's a bunch of the sources. And in the borehole, in the observation well, it's like 4 and 8 meter sensors down to 2 kilometers down the hole. So a lot of data in here. But we wanted to see, could we use Marchenko thing and not even need a borehole at all to get a similar result? Okay, and that's what, so here's the idea. We actually technically didn't need this, but we could make the first arrivals on the VSP to create a velocity model. And then here's a synthetic VSP, vertical seismic profile, in depth, but then in time with all the scattering off of those little layers. And so here, the question is, can I redate them to, here's on the computer, a source at a certain depth. And here is taking that exact same VSP and putting a source down there. And of course, in the borehole, you don't like putting sources in here because you don't want to blow up your borehole, but you don't mind putting receivers down there. So the idea is I can do that component. And so here's an example, then I can do the imaging, and this is just the synthetic example, where this might be where I have one velocity and another velocity where I might have put the carbon in here. And the idea is I can come up with 2 reflection responses and do a differencing to find out where the carbon was injected into the well. I mean, you can do it fancier than that, but this is what we did, several years ago. So, and here's actually one of the VSP gathers of the observed data. And again, with some gain corrections and some various stuff in here. And so then the idea is we can then essentially image it. And let me see here. The middle one is from the corridor stack VSP with all the data, with a dense set of receivers down the borehole. This one is not. And it doesn't have any receivers in the borehole. I don't need a borehole. And then here's my comparison. So again, if a borehole, you guys can tell me what the current price, I made a mistake of underballing what a price of a well is these days, but $50 million, depending on where. Depends.
No, that's a big one.
Oh, a big one would be 50 million.
Oh, it could be 200, but at least onshore.
Yeah.
10 maybe, 5 or 10, I don't know, onshore.
5 to 10 would be.
Okay, but still, if you can get away without it, I mean, that's actually pretty interesting. Anyway, so let me go to the next slide. So then we focused in on where they actually did a CO2 injection. And so the red line is a complete corridor stack before and after injection of the CO2, which is here in the VSP corridor stack. And this is the known depth. And then here with the black line, no receivers or sources in there, and I can get a similar location. So if I'm going to be continuously monitoring, and we had an earlier talk where I put sparse receivers, I have no receivers in there, okay? And so let me see here. Okay, Marchenko imaging of carbon compares well with standard VSP processing without, you know, I don't know, 500 sensors in a borehole, for example. It only requires a limited knowledge of velocity profile to convert for conventional process and does not require a dense number of receivers in the borehole. If I have some, I can use them to my advantage, of course. Okay, general conclusions, ambient noise can be used to obtain images of subsurface, but more research is needed to get similar levels of resolution. Basic stuff, like taking out the ground roll, it's all in there. How do you get it out? Okay, and then other issues too, of really how do you make it look the similar level that people in the 40s and 50s could get back then, okay? And then the second one is for structures in the earth. New interferometric methods are used to convert seismic data into virtual images with higher resolution of Earth subsurface. Okay, and that's it. Let me see how much over. I'm 20 minutes. So I think I'm 5 minutes over. So I raced through mine. So we're kind of close to our coffee break time.